This is a web app that I created to help calculate the Drake equation. Frank Drake is a member of the National Academy of Sciences, where he chaired the Board of Physics and Astronomy of the National Research Council from 1989 to 1992. He was a professor of astronomy at Cornell University from 1964 to 1984 and served as the director of the Arecibo Observatory. He also serves on the Board of Trustees of the SETI Institute. The Drake equation tries to estimate the number of communicating civilizations in the Milky Way galaxy. These are the terms of the Drake equation, and these are the descriptions of each term. If you'd like to read more about the Drake equation, go to Google, search on Drake equation and Wikipedia, and this is what you'll get. Let's go ahead and take a stab at the Drake equation. The rate of formation of stars per year suitable for the development of intelligent life. Let's say 7. The fraction of those stars with planetary systems. Well, we know from Kepler data that most stars have planets. That number should approach 1, so let's say 0.99. The number of planets per solar system with an environment suitable for life. Let's say 0.22. The fraction of suitable planets on which life actually appears. This is where we really have to guess. There's no right or wrong answer in the Drake equation. These are simply estimates based on nothing more than what we think, according to Jill Tarter. So the fraction of suitable planets on which life actually appears, let's make that half. And the fraction of life-bearing planets on which intelligent life emerges, let's say intelligent life emerges 1 out of 10 times. The fraction of civilizations that develop a technology that releases detectable signs of their existence into space. Well, if they become intelligent, and they evolve long enough, let's say at least half will be able to release detectable signs of their existence into space. L, the length of time in years such civilizations release detectable signals into space. Let's say 10,000 years. Hopefully they don't destroy themselves, or some cosmic cataclysm takes them out, such as a comet or asteroid. And let's click estimate for n. We're estimating that 381 civilizations in the Milky Way exist whose electromagnetic emissions are detectable, and the average distance to the nearest communicating civilization would then be 1,191 light years. Here's how we arrive at average distance. Take the volume of the Milky Way galaxy, divide that by n, the number of civilizations using radio, and cube root that to get d, the average distance. Here we have some candidate stars. Kepler-62 looks interesting. Kepler-62 orbits a K-type star. K-type stars are generally less massive and not as bright as G-type stars, such as our Sun. This is a K2b, which means it's one of the hotter K stars, and the V part means that it's still on the main sequence, burning hydrogen, converting hydrogen into helium. It happens to be roughly 7 billion years old. Here you can see this image that I captured from NASA's Eyes on Exoplanets. This is the URL for NASA's Eyes on Exoplanets, and I recommend that you download it. It's a very good program. Kepler-62f has a nice circular orbit within the habitable zone. There are a bunch of other planets closer in to the star, and here's another planet that orbits in the habitable zone, Kepler 62e. Given the star's age and type, these are good candidates for life, at least, if not intelligent life. And that's the Drake equation. I thank you very much.